Today we will explore angular motion, axis of rotation, center of mass, stability, and angular momentum, and how these concepts apply to a range of sporting examples, including a gymnastics analysis. Angular motion is rotation around an axis. For example, an ice skater spinning. When the skater spins, they rotate around their longitudinal axis. Angular kinematics describes motion. For instance, it is used to describe how much a diver rotates during the execution of a somersault. Angular kinetics is the study of forces behind rotation, such as in high jump, the performer arches their back during the execution of a Fosbury flop to clear the bar. The rotation during this movement relies on angular kinetics. Axes of rotation. Axes of rotation are imaginary straight lines that you rotate around during motion. There are three main axes of rotation. First, the longitudinal axis. This runs from superior to inferior part of the body. An example of this is a dancer performing a pirouette, which includes them rotating their body whilst their foot stays spinning at the same point. Secondly, the mediolateral axis. This is from medial to lateral side of the body. An example of this is a diver performing a somersault as they are rotating around this imaginary line at their hips. Finally, the anterior-posterior axis is the imaginary line that runs from the anterior to posterior side of the body. For example, during a cartwheel execution in gymnastics, the performer is rotating around the anterior-posterior axis. Planes of movement. Like axes of rotation, planes of movement are imaginary divisions of the body. There are three types of planes. Firstly, the sagittal plane. The sagittal plane divides the body into medial and lateral, left and right. This plane allows movements such as flexion and extension. For example, the goalkeeper kicking a football for a goal kick, as they are extending their leg at their knee joint. The frontal plane divides the body into anterior and posterior, front and back. This plane allows movements such as abduction and adduction. For example, in gymnastics, when the athlete performs a cartwheel, they are performing abduction at the shoulder joints during the execution phase. The transverse plane divides the body into superior and inferior, top and bottom. This plane allows movements such as rotation. For example, when a golf player rotates their hips during a drive shot, this action happens across the transverse plane during the execution phase. The planes and axes are relevant to each other. For example, the movement of a specific sporting action occurs in a plane around a corresponding axis. Movements that take place in the sagittal plane move around the mediolateral axis, which are actions such as flexion and extension. A sporting example of this is an execution of a jab in boxing. There is extension at the elbow as the performer pushes their fist forward. Movements in the frontal plane occur around the anterior-posterior axis. These movements are abduction and adduction. An example of this is a gymnast performing a cartwheel in the execution phase as their legs are moving away from their medial line of the body. Movements that occur in the transverse plane move around the longitudinal axis. This movement is rotation. An example of this is in discus. The thrower rotates their hips and their torso and shoulders follow with the movement in the execution phase of the throw. This allows the performer to get a full range of movement. Center of mass is a point through which gravity acts on an object, or the point where this is an equal weight force on both sides of the system. The center of mass is symmetrical objects such as balls and in asymmetrical shapes such as the human body. In symmetrical objects, the center of mass is located at a geometric center. However, in asymmetrical shapes, the center of mass changes according to the position of the body. In tennis during a serve, the athlete will keep their feet and shoulders width apart, which increases their base of support. They will also slightly squat down to keep stability due to the athlete holding a racket. Their center of mass will be higher than normal. Therefore, they will squat down to be lower to the floor. The athlete's line of gravity runs through their center of mass, which runs through the center of the body and through the middle of their base. This keeps the tennis player balanced and gives them stability, which will help them have good control over hitting the ball and keep them balanced with the follow-through. They must do this as the human body is an asymmetrical shape, which means the centre of mass does not stay directly in the centre of the body, and this can affect performance if not acted upon. Another example is in football. If a player strikes a ball directly through its centre of mass, it will travel in linear motion, which means it will follow a straight line. If the player strikes a ball above the centre of mass, this will create a topspin and follow an angular motion, which will cause the ball to dip down quickly. If the player strikes a ball below the centre of mass, this will cause angular motion as well, as the ball will stay in the air for longer. Angular motion explains the movement of an object around a fixed axis or the centre of mass, where all parts of the object follow a circular motion. This means that forces applied above or below the system's centre of mass rather than directly through it, causing angular motion rather than linear motion. During a high jump technique of the Fosbury flop, the performer will experience both linear and angular motion. The jumper runs a curved path on the approach to the bar. This converts linear momentum into angular momentum. The dominant foot, which is planted on the ground, applies a rotational force to the ground. Due to Newton's third law, an equal ground reaction force is applied to the jumper's foot, which pushes the performer vertically and horizontally upwards. This creates a backwards rotation, and the performer arches his back, going over the bar head first. Due to the jumper going head first over the bar and arching his back, this means that when he is going over the bar, his centre of mass will be below the bar, allowing him to clear it, as gravity is not acting on the centre of his body. He has manipulated his centre of mass as his arms, legs and head are below the bar, but his body is above the bar. This causes the centre of mass to be outside of his body, allowing him to clear higher jumps. Stability is the ability for a system to maintain or return to equilibrium after a disturbance. The factors that affect stability depend on are base of support, the area beneath a system in contact with the ground, centre of mass position, the lower centre of mass, the greater the stability, line of gravity, the centre of mass must remain within the base of support for balance. An example of this is a defensive stance in basketball. When the attacker applies a direct force to the defender to defeat him, this could cause the defender to lose balance, which will affect their performance. However, if the defender was to have their feet wide apart and knees bent, this will create a large base of support and increase the resistance of being pushed over. Also, bending their knees allows the centre of mass to be lower to the ground, which increases their balance and also controlled lateral movement when defending the opposing player. In this example, the player has manipulated their centre of mass to benefit their performance as they have stayed in control of their body and is still able to experience a great amount of force against them. A poor example of stability would be a goalkeeper in football attempting to make a save. If the goalkeeper starts in an upright position with their feet close together, this causes them to have a small base of support, which affects how much explosive power they can generate to push sideways. If they have set themselves with straight legs rather than bent legs, this will cause a performance centre of mass to be higher above the ground, which will have a negative impact on their balance, causing slower reaction time and a weaker push-off. Finally, if the keeper leans sideways before pushing off, this will cause their line of gravity to shift outside of their base of support as it's too small of a distance. This will cause a lack of power and cause the goalkeeper to fall mid-dive due to a lack of stability. In this example, the performer has manipulated their centre of mass in a negative way, which has impacted the outcome of their performance as they have failed to execute the dive. A lever is a bar that moves a load about a fixed point when force is applied to it. There are four main components to a lever system. Lever arm, which is a bone that is being moved about a point. Fulcrum, which is a joint where the lever arm pivots. Effort, which is the force applied by the muscles to the lever arm. And load, which is the resistance that must be moved. During the execution of a golf swing, the lead shoulder, which is the left shoulder for a right-handed golfer, acts as a fulcrum during the backswing and downswing as the movement happens at the shoulder joint. The movement is generated by the core muscles full of rotational force, legs full of ground reaction force, and arms full of swing acceleration. The load is the golf club's head mass and the air resistance that the performer must overcome during the swing. The club's shaft acts as a lever arm. There are 3 types of levers. Firstly, the first-class lever. This is where the fulcrum is in the middle of the arm, for instance during the execution of a weighted tricep overhead extension. The fulcrum is in the elbow joint, the load is the weighted dumbbells plus the body weight of arm of the performer. The lever arm is the forearm's bones, radius and ulna, and the effort is the tricep brachii, which contracts to extend the elbow. During the preparation phase of a throw-in in football, the performer must act as a first-class lever system. As the player lifts the ball behind her head, the elbow is performing flexion. The fulcrum is the elbow joint. It sits in between the load, which is her body weight of the arm, and the weight of the ball, and the effort, which is the tricep muscle. This is why it's a first-class lever. Secondly, the second-class lever system. This is where the load is in between its fulcrum and the point of effort. During the execution stage of a calf raise, the load is in the center of the lever, which is their feet. This is a person's body weight acting on the base of support. The fulcrum is the last joint in the toe that allows for movement. The effort is the gastrocnemius, which moves the body upwards. Sports that require jumping require your ankle to act as a second-class lever. For example, the takeoff during a long jump. When an athlete pushes off the ground, the fulcrum is a joint in the metatarsals. The effort is the gastrocnemius and soleus, contracting to plantar flex the foot. The load is the athlete's body weight and any external forces. The lever arm is the distance from the ankle joint effort to the ball of the foot fulcrum. Lastly, the final lever is the third-class lever. This is where the effort is in the middle of the lever arm. For example, during the execution stage of a bicep curl, the fulcrum is the elbow joint, the effort is the bicep brachii, and the load is the weighted dumbbell. As the bicep contracts, pulling the arm upwards, the joint moves about the axis and works against the load to overcome the force. During sports that involve flexion, your elbow requires your arm to act as a third-class lever. For example, in volleyball, when an athlete performs a spike during the preparation phase, the fulcrum is the elbow joint, which is flexed as they go to strike the ball. The effort is the bicep brachii, which contracts to flex the elbow before the strike. Then the load is the lower arm of the athlete. In this example, the effort is in the middle of the lever arm. Mechanical efficiency refers to the ratio of work output to energy input during movement. It measures how effectively the body converts mechanical energy into useful work. How we represent mechanical efficiency is by showing the effort arm is greater than the load arm. This basically means that when we have a lever arm diagram, if we were to draw a line vertically up from the center of the fulcrum and then across the length between the fulcrum and effort, it will be a shorter distance than the distance between the fulcrum and load. When we talk about mechanical efficiency of levers, the lever is either a mechanical advantage or a mechanical disadvantage. However, both types are good, they are just better at certain variables. There are 3 types of variables: strength, speed of movement, and range of movement. Levers that are a mechanical advantage are generally good for strength. However, they are not good for allowing a range of movement or speed of movement. The levers that are a mechanical disadvantage are generally good for range of movement and speed of movement, but they are not great at providing strength for movement. When calculating mechanical advantage, we use the equation effort arm divided by load arm to give us a numerical value. If the value is greater than 1, then this means it is an advantage and is. When calculating mechanical advantage, we use the equation effort arm divided by load arm to give us a numerical value. If the value is greater than 1, then this means it is an advantage and is good for strength. This generally goes for second-class levers as they provide movements like jumping, which makes the load your whole body weight rather than just a body part. If the value is less than 1, this means that the lever is a disadvantage, which just means that it is good for a range of movement and speed of movement. This generally goes for the first class and third class lever. The first example is a basketball player during the execution phase of a layup. They are required to use a second class lever, which means the load is in the middle of the lever arm, which is in this case would be the entire body weight. The fulcrum is the joint in the phalanges performing plantar flexion with the assistance of the gastrocnemius, which is the effort. The lever arm is the ball of the foot. We can see that in the diagram, the load has a shorter arm to the fulcrum than the effort. To calculate the mechanical efficiency to get a numerical value, we can use the equation MA equals effort arm divided by load arm. This has given us a value greater than 1, which means that this lever is a mechanical advantage and is good for strength variable, which will help support the athlete during the jump. The second example is a hockey player during the execution phase of a pass. In this example, the effort is in the middle of the lever arm, which makes it a third class lever. The effort is the pectoralis major, moving the fulcrum, which is the shoulder joint. The lever arm is the shaft of the hockey stick, and the load is the hockey puck. In this example, the effort arm has a shorter distance from the fulcrum than the load arm. We can calculate the mechanical advantage by using the same equation as before, which gives us a value smaller than 1. This makes this lever a disadvantage, which means it is good for speed of movement and range of movement, but bad for strength. However, as this is an external system, e.g. a hockey stick, the performer can move the location of the components on the lever arm. For example, the hockey player can move the arm further down the shaft of the stick, which brings the load, the puck, closer to the fulcrum, the shoulder, which then means that the load arm is shorter than the effort arm, which then makes the lever good for strength and allows the player to put more power behind the pass. Internal systems such as the jump and the layup cannot be manipulated, as you are not able to relocate the different parts of your body. Torque is how we measure the force of a twisting or rotating movement, also known as the turning effect. Internal torque is the effect in the body. This is where the muscles are applying an eccentric force at the fulcrum joint to pull the bones. External torque is the effect outside the body. This causes a change to speed of rotation, angular velocity. Torque is a vector, which means it is a magnitude and a direction. The units for torque are Newton meters, and the direction is either clockwise or counterclockwise rotation. There are 3 factors that affect torque. This includes the magnitude of the force applied, the direction of the force applied, and the location of the force applied. We calculate torque by T equals force times movement arm, also T equals F times R. During the execution of a tennis forehand stroke, the elbow is flexed to shorten the movement arm. This reduces the rotational inertia for faster swing initiation. The triceps apply a force of 50 newtons to straighten the arm during the follow-through of the stroke, which increases the racket speed. The elbow to racket distance is approximately 0.5 meters when the elbow is flexed. Therefore, to find a numerical value for torque, in this example, we can use the equation T equals F times R, which would give us 50 newtons times 0.5 newtons, which would then give us a total of 25 Newton meters. This is an internal torque, as the force comes from within the body and creates an eccentric force. Another example is in golf, when the shoulder rotation during a drive shot. The shoulder rotates, which increases the acceleration of the golf club. The pectoralis major applies a force of 100 newtons. The lever arm is a total distance between the golfer's arm and club, which is 0.7 meters. We can find a torque the same way as we did before, by doing 100 newtons times 0.7 meters, which gives us a total of 70 Newton meters. This is the internal force from the muscles that generate a larger acceleration in the swing by rotating the arm during the execution of the shot. Gymnastics analysis. Angular motion. During the execution of a 360-degree wolf turn on the beam, the athlete starts in a squat position with one leg bent and the other extended. The gymnast rotates on the bent leg, using the foot in contact with the beam as the pivot point along the longitudinal axis. Planes and axis. During the execution of a cartwheel on the floor routine, the gymnast rotates around the anterior-posterior axis, which runs from the anterior to the posterior part of the body. The gymnast also performs this movement along the frontal plane during the skill. The gymnast's arms and legs are abducted away from the medial line of the body. This helps them execute the skill efficiently and allows for specific adjustments to improve stability and control. Center of mass and stability. During the execution of a handstand, the center of mass is higher up on the body as the arms are fully flexed, so the arms are further away from the body. However, the center of mass is still in the center. During the handstand, the line of gravity must stay aligned within the base of support. The base of support in this case is distance from the left hand to the right hand. A slightly rounded and engaged core keeps the line of gravity in line with the base of support, keeping the performer stable. However, if the performer was to lean forward by pressing on their fingers tips, this would cause the center of mass to move on the body, which shifts the line of gravity outside the base of support. If they lean backwards, this will also cause a movement in their center of mass and move the line of gravity outside the base of support, which in both cases would cause them to tilt or fall backwards or forwards. Levers. During the preparation of a handstand on the vault, the gymnast must sprint towards the vault and use an explosive plantar flexion during the final stage of the vault takeoff. This explosive jump requires a second-class lever, which means the load is in the center of the lever arm. The load in this example is the weight of the gymnast's body. The fulcrum is the ball of the foot. This is the joint that allows the movement. The effort is the gastrocnemius and soleus. This is what propels the body upwards. We can calculate the mechanical efficiency of the jump by using the equation MA equals effort arm divided by load arm. The effort arm is 0.05 meters away from the fulcrum, and the load arm is 0.03 meters away from the fulcrum. Therefore, this gives us a mechanical advantage of 1.7 meters, which is greater than 1. This means that this lever is good for strength, which is why the athlete can propel upwards efficiently and advantage. Torque. During the execution of a giant swing on the high bar, the gymnast uses torque to keep control of rotation. The joint torque hip flexors contract to keep the body fully extended in the upwards and downwards phase of the rotation. The hip flexors apply a force of 150 newtons to keep the body extended during the movement, which increases control. The distance from the bar to the gymnast is 1 meter. Therefore, to find a numerical value for torque in this example, we can use the equation T equals F times R, which would give us 150 newtons times 1 meter, which would then give us a total of 150 newton meters. This is an internal torque as the force comes from within the body and creates an eccentric force. Thank you for listening.